All right, welcome back everyone. Today, we are diving into a really high-yield masterclass. We're targeting a highly specific and honestly undeniably crucial area of the Cambridge AS and A-level computer science syllabus. Specifically, we're looking at subject code 9618, embedded systems, with an intense focus on their benefits and drawbacks. Now, before we jump into the deep end of exam strategy, let's just make sure we're all on the same page and establish our baseline. What exactly is an embedded system? Well, it's essentially a dedicated, purpose-built computer system that's integrated inside a much larger mechanical or electrical framework, all to perform one very specific task. Think of the microprocessor inside your washing machine at home or the anti-lock braking system in your car. But here's the thing. Today, we aren't just going to sit here and recite a boring list of facts about them. No way. We are going to decode exactly how you prove your true understanding to the examiners. If you want to transform your approach from just blind rote memorization into a dynamic, mark-winning strategy, you are in the perfect place. So let's dive right into this.
So why do students find evaluating algorithm efficiency so incredibly hard? It's a fantastic question, isn't it? And honestly, it's the elephant in the room when we talk about embedded systems. This specific reality appears in every single examination series. I mean, the stakes literally couldn't be higher. Because embedded systems are defined by rigid physical constraints, maybe it's running on a tiny little coin battery or operating with just a few kilobytes of processing memory. The efficiency of your algorithms isn't just some abstract theoretical concept, it's real. When you're asked to evaluate these systems on an exam, you are actively defending the logic of your code within those strict physical limits. And that right there, that is exactly what trips up so many students. Okay, here is our roadmap for today. We are completely opening up the examiner's playbook. We'll start with the Embedded Systems Challenge, then move into core theoretical principles, break down the technical methodology framework, cover some critical evaluation strategies, and finally, look at the top examiner warnings straight from the source.
Section 1. The Embedded Systems Challenge.
Listen, I cannot emphasize this enough. Understanding the benefits and drawbacks of embedded systems is completely unavoidable if you want to succeed in the 9618 exam. It is a foundational pillar of the syllabus. But here's the catch. The challenge isn't just knowing the textbook definition. The real challenge is articulating exactly why a specific system is beneficial or restrictive in a highly specific context. Let me give you an example. A processing delay of, say, 1 millisecond? That might be a totally acceptable drawback for a smart thermostat in your hallway. But that exact same 1 millisecond delay, it's a literal fatal flaw for a cardiac pacemaker. Examiners aren't looking for a Wikipedia summary. They are hunting for your ability to apply deep technical knowledge of things like power consumption and memory limits to dynamic, real-world scenario. Oh, and before we continue to the theoretical principles, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2. Core Theoretical Principles. All right, let's look at what's actually happening behind the scenes of the exam. Cambridge requires much more than just reciting facts, right? They actually target 3 distinct cognitive domains. First up, knowledge and understanding. This is your baseline. It's simply knowing the core concepts of embedded systems. But then we step up to application. Here, you need evidence-based reasoning in specific scenarios. You have to prove to the examiner why a drawback, like high power consumption, actually matters in the real-world context they gave you. Finally, we hit analysis. This is the top tier, where you are evaluating algorithm efficiency. How does your specific code solution impact the heavily limited resources of an embedded device? Seeing this structured approach really shows that superficial knowledge simply won't cut it.
Take a look at this quote. The assessment framework prioritizes analytical depth over superficial breadth. This right here is the academic benchmark you absolutely must meet. Put yourself in the examiner's shoes for a second. They would much rather read a deeply reasoned, logical argument about 2 specific processing drawbacks of a smartwatch than read a bulleted list of 10 random facts with absolutely zero context. Logical, structured reasoning will always score higher. It shows the examiner you understand the why and the how, not just the what.
Section 3. The Technical Methodology Framework.
Okay, let me introduce you to a concept that is going to completely change how you write your answers. It's called the method mark strategy. This is essentially the art of earning exam marks through a demonstrated procedural process, logical step-by-step decomposition, and crystal clear working. Here's the secret. Examiners actively reward your algorithmic thinking process. Even if your final conclusion has a slight flaw in it, if you explicitly write out your analytical framework and show them exactly how you deconstructed the hardware limitations, you are scooping up valuable method marks all along the way. You have to make your thinking visible on the page. And hey, stop scrolling for just a second. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions.
So to guarantee you're capturing those method marks, you need a standardized sequence. I highly encourage you to adopt this 5-step process for tackling these questions. Step 1. Deconstruct the question. What is it really asking you to do? Step 2. Extract the relevant data from the scenario. Step 3. Select your analytical framework. Are we talking about real-time processing constraints, battery life, or maybe hardware costs? Step 4. Execute your analysis with clear notation. And Step 5. Present your final answer using correct, formal terminology. If you adopt this algorithmic approach to your exam writing, it will make your responses instantly tighter and so much more professional.
Within that framework we just talked about, there are specific practical application skills you have to demonstrate. When you analyze an embedded system, your algorithmic thinking must include step-by-step decomposition. You also absolutely must justify appropriate data structure selection. Remember, microcontrollers have heavily restricted memory limits, so choosing a massive, inefficient array, that is a major drawback that you need to identify. You must consider efficient code implementation, rigorous testing, and even extracting data from binary representations. These aren't just random programming skills. They are the exact criteria you use to evaluate the embedded system itself.
Section 4. Critical Evaluation Strategies.
When you are hit with a question asking you to critically evaluate an embedded system, you must build a case that examiners literally cannot ignore. It's a deconstruct, solve, evaluate sequence. First, you identify the given information, break the problem into logical steps, and solve it systematically. Then you check for reasonableness. And finally, actually, scratch that. This is absolutely the most important part. You make justified recommendations. Think back to the car example. If an embedded system is running an anti-lock braking system, checking for reasonableness means understanding that even a fractional delay in processing wheel speed is a fatal drawback. Your recommendations must be firmly justified by those real-world constraints.
Evaluating alternatives and comparing different approaches must always hinge on these 4 specific criteria. Time complexity. Basically, how fast does it run? Space complexity. How much memory does it eat up? Edge cases. What happens under extreme or highly unusual conditions? And finally, the effect on overall performance. You can't just write down, "This algorithm is bad." That gets you nowhere. You must say something like, "This algorithm has high space complexity, which is a significant drawback for an embedded system with limited RAM, negatively affecting its overall real-time performance." See the difference? That is exactly how you secure top marks.
Section 5. Top Examiner Warnings.
We are now looking at the insider scoop. According to the principal examiners themselves, here are the top 3 mistakes students make year after year. Number 1, providing vague details that completely lack technical depth. Number 2, entirely forgetting to consider boundary conditions in edge cases. And number 3, and this is the most fatal error of all, ignoring the specific context given in the question. Listen, examiners are practically begging you to stop doing these 3 things. These are the exact pitfalls where marks are needlessly thrown away by students who actually know the material, but just fail to present it correctly. Let's contrast the wrong way with the right way. Instead of writing a generic answer that lacks technical depth, like simply stating, "Embedded systems have low memory," which, by the way, earns you almost nothing, you must provide justified recommendations explicitly linked to the scenario. For example, you should write, "Due to the limited 2 KB memory of the embedded microcontroller in the smart thermometer, utilizing a complex recursive sorting algorithm is a drawback as it risks a stack overflow." Do you see how much better that sounds? Specific context is the ultimate key to unlocking maximum marks. I'm going to read this directly to you. Examiner alert, the classic mistake is providing generic answers. Always link every point to the given scenario. You need to anchor this rule deep into your exam strategy. If your answer could apply to a microwave, a car braking system, and a smartwatch equally, well, your answer is far too generic. Fix it immediately. Anchor your technical knowledge to the specific constraints of the scenario provided on the paper. To help you organize all these benefits, drawbacks, and constraints for rapid recall during a high-pressure exam, I want to give you a quick memory hack. Create a personalized acronym for the factors affecting embedded systems, things like power consumption, processing limitations, memory constraints, and real-time requirements. Build an acronym that works for your brain. When you sit down and turn over that exam paper, write your acronym right at the top of the page. That way, you instantly have a technical checklist to pull from when you're formulating those beautiful, context-specific answers.
So, what's it going to be? Will you rely on generic answers hoping that are just good enough? Or will you use the examiner's playbook to logically, systematically extract every possible mark? The choice is entirely yours, but I think we both know which path leads to the grade you actually want. Take these strategies, practice them on past paper questions, and make them second nature. And remember, students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep analyzing, keep evaluating, and keep learning. See you next time.